All right, can everyone hear me? I'm hoping so. No, nothing. Yes. Thank you guys. All right, so welcome to the review session. Again, this is one of two. You guys were particularly good in the the middle part of this course, so of course we're going to have two review sessions. Today we're going to cover the 2014 midterm 2, and then tomorrow we are going to cover the 2015 midterm 2. Now I'm looking at the time, and I realized that 5 o'clock may not have been the best choice. Some of you may have had labs or something like that. So just a quick question for those who are here, all I guess 13 of you. For tomorrow, would you prefer to have the midterm review around 5:30? Would that work better? I'm not too sure.
Yes, please.
Yes? Okay, perfect. So tomorrow will be 5:30. I'll send an announcement to everyone. And again, for those of you who aren't here right now because you're in the lab, I'm really sorry, but don't worry, I have it recording, and of course it will be uploaded tonight. So nobody should theoretically miss out. Now, I do have a quick question because I heard about it so much that I've become quite curious. How did 330 go? Civi 330, water. I've heard so much about it that I'm so curious how you guys found it. Oh, you guys look like just the first years right now. They just got their... when you guys took Eng 130, was it one midterm or two? For me, it was one, but I'm not sure. Yeah, so you guys are all the same as me, but in order to try and make it more forgiving, they split it up into two midterms, and they just got their second one back today, and it's a dumpster fire. They're all losing their mind because apparently the average was 50% or something like that. It was quite a mean midterm apparently. I'm sorry that you guys had to deal with it. I told the Eng 130 students it gets better, but now after your response, I'm not too sure. So we'll have to wait and see. Hopefully my midterm here in 398, hopefully that goes a little bit better. So we're going to begin. Just a quick little disclaimer, I have to do this. I'm going to put the chat on the recording screen. Does anyone have a problem with their name being shown? Anyone with a problem? It's just your name that will be shown on the recording. It won't be anything else. I'm going to give you guys a couple seconds. Anyone? All right. So I'm going to put it on screen. If you guys are uncomfortable, just let me know and I can fix it later. All right. So we're going to start the midterm. Now, one thing that I'm going to have to say, because I've been looking through them all, these came from Dr. Sammer, of course. Some of you guys may know him, some of you don't. He's a brilliant guy, and these midterms came from him. Now, Dr. Sammer, when he did this course, it was cumulative. So some of this midterm, as you guys will see, it does cover topics that are directly from topics 1 and 2, the linear algebra portion. As I said, we're not going to test those directly this year, so I will make mention of those types of questions that you guys will definitely not see on your midterm. There's also a couple topics that Dr. Sammer liked to touch upon that is directly related to things like stress and strain, but I didn't really teach them. So, of course, those topics, if I didn't teach them, I'm not going to test you guys on them, and I'm going to make note of that throughout this exam. So, if there's a question that I know will definitely not be on the exam, I'm going to tell you guys. I don't want you guys worrying, saying, hey, Clayton, you never taught me this. Why is it tested? Don't worry. I would never do that to you guys. All right, so we're going to begin. If you guys have questions, you guys have the chat right here, or you can unmute yourself, whatever works best for you. Is there any questions before we begin? I should probably ask that. No? All right. Let's begin then. If you guys do have questions, again, I got the chat. You guys can see the screen all right? I'm hoping so. See the screen? Yeah? All right. Thank you for answering. So this midterm was 24 questions. Again, yours will be 26. Now you guys are saying, Clayton, 26? I thought it was 25. It's 25 questions with one bonus question. Okay? One bonus question. If you guys get the bonus question, it's extra marks. If you don't get it, it's kind of no harm, no foul sort of scenario. As you guys just see, the bonus question is, it's really nice. You shouldn't have a problem with the bonus question. All right? So let's begin. question number 1 here says, a position function of a continuum follows the relationship, and it gives us the 3 position functions x1, x2, as well as x3. It says, then the component epsilon 1, 2 of the infinitesimal strain tensor is... So basically, this type of question is asking us for the small strain tensor. Anytime you guys see this infinitesimal, this right here is saying the small strain tensor. So this question is actually quite a bit of work. As you'll notice, it's kind of off to a bad start, because we know that in order to get the small strain tensor, we need to go from position functions to displacement functions to displacement gradient, and then displacement gradient to strain tensor. So it actually is quite a bit of work. It's a mean question to start off with, and I just want to tell you guys that not all questions will be this much work, so it's not going to be too bad. So we're saying, okay, we are given our 3 position functions, x1, x2, and x3, and we know that if we want a displacement function, which we call u, it's simply going to be our position function x subtracted from big X. So all we're basically doing is subtracting big X1 from small x1, big X2 from small x2, and big X3 from small x3. So I'm just going to put, okay, if we know these, our u is going to be equal to, and I'm just going to put my bracket, what is u1 going to be equal to? Throw it out in chat. What do you guys think u1 is going to be equal to? Let's test you guys. u1. Yes, exactly. All we're doing is subtracting big X1 from that first function. So if we look at this first function, it's already 1.001 big X1. So if I subtract 1 from that, I get 0.001 big X1. Thank you for answering. So we know it's going to be 0.001 big X1. And then the big X2, well, nothing really happens to it. So it's going to be plus 0.002 big X2. If we go down to the next one, small x2, again, all we're doing is subtracting big X2 from this. So it's going to be 0.00, I guess in this case 2, times x2 plus 0.003 times x1 in this case. Now the last one's nice and easy. We have x3 and we're subtracting x3. Well, we know that's going to be 0. And what I'm going to do really quick, and you guys will probably see me do this a lot, is I'm just going to try and move it so it gets more on screen. I'm very bad with space management, as you guys are seeing. So it's going to look something like this. And now this is great because if we have our displacement functions, we can then find our displacement gradient, which we call nabla u. And remember, nabla u is just going to be a bunch of partial derivatives with respect to big X1, big X2, and big X3. So for the first row of nabla u, we are going to look at the first displacement function. So it's going to be this one up here. And the first entry is going to be that function derived or taking the derivative with respect to big X1. So if we look here, we got 0.001 x1. So if I take that derivative, we know it's going to be 0.001. And then it's plus 0.002 x2. So the thing to keep in mind is if it's an x2, but I'm taking the derivative with respect to x1, well, it's just going to be 0. So our first entry is just going to be that 0.001. If we say, okay, that's our first entry, our second entry is going to be the derivative of that function now with respect to x2. So the first entry is 0.001 x1. Well, if I take the derivative with respect to x2, that's 0. But then that second part, the plus 0.002 x2, if I take the derivative of that with respect to x2, then I just get 0.002. Just like that. I know it's really boring. I'm trying to over-explain it so that no one has problems. Of course, if I were to take this with respect to x3, it's just going to be 0. So that's how we get these rows of nabla u. If I want the second row of our displacement gradients, I just look at the second function. And if I were to go down it, I say, okay, if I were to take the derivative with respect to x1, it's just going to be 0.003. If I take the derivative with respect to x2, 0.002. And then finally, our last one with respect to x3 is going to be 0. I'm just going to erase it really quick so no one gets confused. The highlighting, come on. There we go. And then finally, the last function is 0, so it's pretty obvious that all three of these are just going to be 0. So that's our displacement gradient. And once you guys have this, the rest is gravy, because our strain tensor is equal to 1/2 of nabla u plus nabla u transpose. So we can find that whole strain tensor, and more specifically, if I'm looking at specific components, so for instance, in the first question here, it said it wants epsilon 1, 2, and in the second question, it says it wants epsilon 1, 1. It's very easy to figure out these components. So epsilon 1, 2, if I were to just do it by hand, chances are you guys are going to throw it into Mathematica. This is just going to be 1/2 of 0.002 plus 0.003. So this is still for the first question. I'm just running out of room. Oops. And if I were to just throw this into my calculator or whatever, or if just looking at it, it's pretty easy to see it's 0.0025. So for question 1 here, the strain component epsilon 1, 2, it's going to be equal to B. And we can just carry this on, because if we look at question 2, it says the position function above, what is epsilon 1, 1? Well, we know that epsilon 1, 1 is just going to be equal to 1/2. And this is pretty trivial, but it's going to be 0.001 plus 0.001, which is just equal to 0.001. So we know in this case, for this question, it's going to be equal to D. So it's quite a bit of work for just 2 questions. This was back in the day when these were written in person, so there was no Mathematica or anything like that. The nice thing for you guys is over your assignments, you guys have developed Mathematica codes. Very well, actually. So what happens is chances are you guys would just input the position functions and the code would do the rest. It'd give you your strain tensor. You guys are all happy. But this is kind of the first basic question that we covered after our first midterm, which is how do we go from position functions to strain gradient? So is there any questions concerning question 1 and 2? Or are you guys feeling pretty confident about this? I'm hoping so, at least. This is one of the harder questions too, believe it or not. All right, everybody's happy. Well, at least I'm assuming you guys are happy. Chances are you guys are not happy, but just remember, 4 more days and reading week, right? 4 more days, 4 more painful days, reading week. Then everyone's happy after that. I know that you guys have my midterm standing in the way, but you guys will do great. I promise you all. All right, so let's look at question number 3. It says the stress at a point inside of a continuum is given by the following matrix, where A, B, C, and D are real numbers, and if S is basically a 3x3 matrix, and it's the deviatoric stress matrix, basically what is it? Now, the deviatoric stress matrix is quite simple to find. S, in its most simplest form, is going to be our stress tensor sigma, which we have above, subtracted from the hydrostatic stress multiplied by the identity matrix. And if we look here, sigma, well, we're given that. The hydrostatic stress we don't know, but we do know the identity matrix. The only unknown that we actually have is our hydrostatic stress, which I'm going to call P. Now, P is nice because P is just going to be the trace of sigma divided by 3. This is the definition of it. So all I have to do to find this hydrostatic stress is just take the trace of our stress tensor. So we know that the trace is the diagonal components all added together. So what we end up getting is we get B plus B plus B, and remember, it's all divided by 3. This is basically an indication of the average compressive or tensile stresses on our body. So if we go B plus B plus B, that's 3B, and then we divide that by 3, we know that this is just going to be equal to B. So in our formula now, S is basically equal to sigma minus, and I'm just going to draw it out because then it becomes really easy, P times I is just going to be B, 0, 0, 0, B, 0, and 0, 0, B. You guys are looking at this thinking, Clayton, it's taken forever. It's so obvious. But basically, all we're doing is subtracting B from all of our diagonal components. And if we look at our diagonal components up at the top here, they're all B. So of course, b minus b, well, all of our diagonal components are now going to be 0. So the answer is going to be D. Is that clear to everybody? The trick with this one, and the only time I've ever seen students mess up, is when they're going too fast. When they go too fast, chances are they forget the 3 at the bottom. And that's where answer B and answer C kind of come from. If you forget that 3 at the bottom, you're in for a bad time. So make sure that you don't forget that 3 at the bottom. I'm hoping everyone's happy with that. Well, maybe not. We'll see. So this is a good question. All right, so we're going to move on. Again, if you guys have any questions, just throw them out in chat. I'm constantly looking at it, but you guys are pretty silent. Maybe you're sleeping, something like that. I don't know. All right, so let's go to the next question. It says the shown figure represents a specimen under a confined compression test. The vertical stress is 200 MPa while the confining pressure is kept at 100 MPa. It says what is the maximum shear stress inside of the specimen? So the first thing that happens with these types of questions when you're given a picture is you're going to have to figure out the stress tensor. So we're going to say, okay, sigma is going to be equal to, let's put brackets like this, and our first component, sigma 1, 1. What do you guys think sigma 1, 1 is? And I'm going to define my axis as follows. As you guys will see for shear, it doesn't really matter, but I want you guys to answer me this. So these are my axes. This will be 1, this will be 2, and this will be 3. What is sigma 1, 1? Let's see what you guys think. What is sigma 1, 1? Negative 100? Absolutely correct. It is negative 100. So the trick I was looking for is that you guys recognize that since we are compressing the cylinder, it's going to be negative 100 and not just 100. The rest we can do the exact same. So we know that for sigma 2, 2, it's going to be negative 200. And then sigma 3, 3 is negative 100. The rest, of course, are just going to be equal to 0 because we're not shearing this in any particular way. And, oops, I'm going to have to move it over a little bit. Running out of room yet again. Something like that. So you guys may be saying, Clayton, well, what happens if you give me shear? We never covered an example where you give me a picture of something shearing. Well, don't worry. If I haven't shown you an example, I'm not going to test you guys on it. So you don't really need to know it. This is as bad as it's going to be in a sense. So now we have our stress tensor. And we know that the maximum shear stress, Tm, is going to be equal to 1/2 of the maximum difference between the principal stresses. So it's going to be sigma 1 minus sigma 2, comma, sigma 2 minus sigma 3, comma, sigma 1 minus sigma 3. So these are the principal stresses. Now, question for you guys in the chat. Do you have to modify your tensor in any sort of way? Or is it already good to go? Do we have to modify that tensor? What do you guys think? Do we have to modify that tensor we have above? Or is it good to go and I can just start subbing in values? It's a hard question. All right, you guys are a little sleepy. That's okay. I know it's Monday. The answer is we don't have to modify the tensor because we don't have any shear components. So technically, these would be the actual principal stresses. The key thing to keep in mind is that let's say that instead of 0, let's say that we had some shear stresses. Let's say that we had 50. The key thing to keep in mind when we're doing this idea of maximum shear is that I would actually have to diagonalize our tensor before going to this formula. That's if we have shear stresses. But we are very lucky in that we don't have shear stresses, so these would be 0 as well as 0, so we can just start subbing in values. And what you guys will find is that Tm is equal to 1/2 of the maximum, and I'm just going to put in the values because it's pretty simple, of 100, 100, and 0. So again, I just substitute the 3 values of stresses I have into that formula. So we know that the maximum one is going to be one of the 100s. And when we take that 100 and then divide it by 2, we get 50 MPa. So how's that sitting with you guys? So far so good? I'm hoping so. No? Still sleeping? That's okay. What do we got? We got 16 people here. That's probably my fault since I did this at 5 o'clock. Half you guys are probably still on the train coming home. I apologize for that. Little secret, I don't have to go to school on Mondays. So it's nice for me, but it's probably pretty bad for you guys. So I apologize for that. So now this question, I'm going to give you guys a hint. All right, give you guys a hint, especially for those of you who showed up. This is a very good question. This would be a fantastic question to have on the midterm. Right? Fantastic question. It's such a good question. It'd be a real shame if you guys did not know this question. Okay? We're going to discuss it right now. It says, the shown figure represents a specimen under a confined compression test. The vertical stress is negative P, where P is a positive real number, while the confining pressure is applied by ensuring that the specimen does not expand or contract laterally. That's going to be important, so I'm going to highlight that right there. It says the specimen is an isotropic linear elastic with a Young's modulus E and Poisson's ratio nu. So here's the key here. If I am compressing a cylinder, right? I'm compressing a cylinder, and I know you guys can't see me, but I'm compressing nothing, compressing my water bottle. And if it is not allowed to expand or contract laterally, what should my lateral strain be? If I'm not allowing it to expand or contract, what should my strain be? What do you guys think? If I don't let something expand or contract, what would the strain be?
0.
0. Exactly. That's the trick. So again, the coordinate system could be however you want to define it. Oops, still on the highlighter. So let's say that I'm going with kind of the traditional one that we've seen, where this is 1, the vertical is 2, and this is 3. What this statement would mean is that my lateral strains, so this would be epsilon 1,1 and epsilon 3,3, they should be equal to 0. All right, so that's the key here. Without that insight, this problem actually becomes almost impossible to solve. Because if we look at our stress tensor, that's another thing we're going to have to do. We're going to follow the exact same procedure before. So in the 1, 1 direction, well, we're not too sure. We just know it's confined. So I'm just going to put C and 0, 0, 0, 0. We know in the vertical direction, I'm applying a pressure negative P, 0, 0. And then, of course, laterally in the other direction, we still have that confining pressure C. So the whole goal here is to say, okay, what is this confining pressure? That's what we're trying to solve for. We're trying to solve for C. Now, since we know our material is linear elastic, if I were to look at one of these strain formulas, so let's say we're looking at epsilon 1,1. We know that for a linear elastic material, epsilon 1,1 is going to be equal to sigma 1,1 over E minus nu times sigma 2,2 over E minus nu times sigma 3,3 all over E. And then from there, I can start plugging in everything. And the key thing to keep in mind, and I'm going to highlight this in blue because this is the key to the whole question, is we know that this strain must be equal to 0. That's the trick here. The strain must be equal to 0. So let's just start substituting in numbers because we have our stress tensor. Nu and E, we're just leaving them as such. So for sigma 1,1, we know that's just going to be C divided by E. Then we go minus nu, that stays the same. Sigma 2,2 we know is negative P, so I'm just going to put P here and then change this to a plus sign. And we know that this, of course, is over E. And then at the end, we have negative nu times sigma 3,3, which was that confining pressure C divided by E. And this is all, of course, equal to 0. So now what I'm going to do is I'm going to rearrange the terms a little bit. The first thing I'm going to do is I'm going to take that term with the P and I'm going to move it over to the other side. So we know that we are going to get something is equal to negative nu times p divided by e. And on the other side, my two terms that I have remaining, both of them have a c over e. So I'm going to factor that out, and we're going to say c over e. And if we look, it's going to be 1 minus nu. Now, if I were to compare these two expressions, both of them have the Young's modulus at the bottom. So I can cancel out the Young's modulus on both sides. And then all I have to do to isolate c is just go divide by 1 minus nu. So you're going to see that the confining pressure is negative nu times p divided by 1 minus nu. It's going to be just that. And if we were to look at our two, I can't speak, I don't know why. If we were to look at our different options, we can see that this option that we just derived is the same as option A. So that's going to be our confining pressure. Really good question. It'd be a real shame if this came up on the midterm and you guys forgot. Now, here's another juicy piece of information. Extremely juicy. Those of you who came today, you guys get the good stuff. When we look at this answer and we're finding this confining pressure, we said that it's going to be negative nu times p divided by 1 minus nu. In theory, do I need my Young's modulus to solve for the confining pressure? What do you guys think in the chat? Do I need a Young's modulus to solve this question? No. That'd be another key piece of information to remember for the exam. I love dropping hints. I'm not sure if you guys like dropping hints, but I like dropping hints. It's a lot of fun. All right. Well, actually, it's kind of painful. The worst thing that happens is when you drop a hint and then students still get it wrong. It's like a dagger to the heart. I'm sure that won't be you guys. You guys know everything, so it's good to go. Now, if we look at question 6. Question 6, hold on one second. So in this question, compression is positive. We have the compression as negative. And that confining pressure, if you were to substitute values in, you will find that it's a negative. We have the compression as a negative. So it isn't positive, so I'm not too sure what you mean by that. I'm hoping I answered your question. I'm not too sure. We had the negative sign on the P to account for compression. And if you were to substitute values into the formula, it kind of depends on the elastic modulus, or not elastic modulus, the Poisson's ratio. Because if our Poisson's ratio expands or contracts something, it creates two whole different scenarios, as you will see. So yeah, perfect. In the tensor, C doesn't have a negative sign because it represents the confining pressure. Yes. So what basically happens is this, is the whole confining pressure that we have here, C, it depends on the Poisson's ratio nu. Because if I were to compress something and it expands, then I need a compressive force to keep it from expanding. But if I were to compress something and it has a negative Poisson's ratio, well, then we know that it is also going to shrink. Well, in that case, I need a confining pressure that pulls it in tension to keep it from expanding or contracting. So it's all dependent on the Poisson's ratio nu. It can be 1 or 2. If I were to give you a question like that, I'd make it pretty obvious. So you guys are thinking about it too much. That's another thing about dropping hints, is that students start overthinking it. Don't overthink it. I'm not that mean. I'm not going to give you something so crazy. All right. So we're going to move on. This question, again, what I kind of said at the beginning, there are going to be questions that appear from the first midterm. I'm not going to do that. We know that this will not be tested on our midterm because this is something we covered before, but we're still going to go through it. We might as well have an entire or a complete exam breakthrough. So it says, let f be a function from r to -1 to -1, such that f of x is equal to sine of x. So what I'd like to do in these type of questions, of course, is draw out our function. And I'm just going to draw it like this. This is all we'll need. And let's see how much you guys remember. Again, this will not be on the test, But let's see what you guys remember. So sine we know is going to look something like that. And we know that if we were to plot it, it goes from 1 to -1. And basically it's asking if it is injective, surjective, or bijective. Now again, will not be on our test, I promise you. But let's see what you remember. I'm going to ask you guys, is this function surjective? No, let's start with the basics. Is this function injective? What do you guys think? Is this function injective? It can be pretty difficult. Is this function injective? Nope. Exactly. Thank you for answering. So for injective, remember, we always do kind of the horizontal line test. If I were to draw a horizontal line, well, there is a spot, and it kind of bumped up. Actually, let's go to pink. I've already used pink. Let's go to green. It intersects our horizontal line twice. So because of that, we know that it is definitely not injective. Now, if something is not injective, can it be bijective? If something is not injective, can it be bijective? No, exactly. So this also goes away. So the last one we're left with, is this thing surjective? What do? Well, we look at, does it account for all of these values? Can I, from this function, get any value between -1 to 1? Is every value between that range accounted for? Or within that range? Yes. So this would be surjective. All right. So again, that won't be tested, but it's always fun to go over. Another thing that will not be tested because I forgot to include it in the lecture notes, and you will see this in a couple midterms, is the idea of true stress. True stress. It's actually very simple. Again, I just forgot to add it into one of the lecture notes, so it won't be on the test. I guess I'll do kind of an X here. And it's very simple though. It says in a tensile test of a steel specimen, the engineering stress was measured at 350 MPa, while the corresponding engineering strain was measured at 0.1. What is the true stress? As I said, it's very simple. The true stress of something is going to be equal to the engineering stress multiplied by 1 plus the engineering strain. And that's it. So if you guys were to have this question on your test, all it would be is just substituting 350 for the engineering stress, and then 1 plus the engineering strain, which we had as 0.1, and you get 385. And that's it. So it's kind of a shame that this isn't on the exam because, as you guys can see, it's a pretty simple question. Not too bad. So again, won't be on the exam. Don't have to worry about that one too much, but for purposes of the review, I wanted to show it anyway. So let's go on to the fun question. This is an absolute great question. This is one of those questions where if you know the trick, everything is easy. If you don't know the trick, you can still solve it, but it's going to take a while. It says, if the stress matrix in a three-dimensional state of stress is represented by, and it gives us a nice Cauchy stress tensor, where P is a real number and greater than 0, then the normal stress on a plane perpendicular to the direction of the vector u, which is PPP, is equal to what? So here's the trick. If we were to look at our state of stress, what type of stress is this? Who remembers? What kind of stress is it when my diagonal components are all the same and everything else is 0? Exactly. It is hydrostatic. So this is a hydrostatic stress state. And if you guys remember, in one of the examples we did in our class, we actually talked about this. For a hydrostatic stress state, the normal stress is always going to be one specific value. So A, B, C, or D. What do you guys think this is going to be? I'll show you the long derivation after. I wouldn't tease you like that, but I'm curious. What would this answer be? What is going to be my normal stress on any plane? Or the plane perpendicular to you? No? Exactly. It's P. It's just equal to the hydrostatic stress. So again, if you guys were to look at this and say, okay, I have a hydrostatic stress state, well then the answer is just going to be P. It's nice and simple. If you guys don't remember it, it's still fine because we can do this the old-fashioned way where we kind of derive it. So we say, okay, we know that we have a normal vector, which is going to be P, P, P. And question for you guys, when we deal with these stress states, typically do we have to normalize our normal vector? Do you guys remember? If I'm dealing with, let's say, a traction vector, do we have to normalize it? Yes. So this is our normal vector, but we're going to have to normalize it. So I'm going to find the magnitude, and what you will see is that it is equal to root 3 times P. So kind of messed up here. It's equal to root 3 times P. So what happens is once we normalize our vector n, it's going to be every component divided by root 3p. So p divided by root 3 times p, well, it's just going to be 1 over root 3, and it's going to be the same thing for everything. 1 over root 3, 1 over root 3. Now, once we now know what our normal vector is, we can find our traction vector. So our traction vector, Tn, is going to be our Cauchy stress tensor, well, technically the transpose of it, multiplied by that normal vector. So if we were to go down the list, what you'll see is that every component is going to be the same. It's going to be P divided by root 3, P divided by root 3, and finally P divided by root 3. Starting to get lots of fun, right? Now, the last part would be the normal stress, sigma n, which is our traction vector, Tn, dotted with our normal vector. So we're basically just taking each component, multiplying them together, and then adding everything up. So if we were to look at this, and our first component is P over 3, and then we were to multiply that by the first component of n, we have P divided by root 3 multiplied by 1 over root 3. Well, what we end up getting is just P divided by 3. And since every component is the exact same, this basically just repeats 2 more times. P over 3, P over 3, P over 3. So it's just going to be equal to P. So again, it's one of those things that if you know the trick, it comes quite fast. If not, well, it's not too bad. All right, so is there any questions about this one? Again, worst case scenario, you forget. You just throw it all into Mathematica. You can solve for it all yourself. Does the direction of the vector matter? So it's one of those ones that it doesn't, because basically what happens is we have equal and opposite forces. So what's going to happen is if we have our vector like this, n, we are going to find sigma n in this direction. But then on the other side, if we have the direction backwards, well, it's going to be equal and opposite. That kind of thing, sigma n. So it doesn't really matter, no. All right. So we're going to move on to the next one. And if you guys have, well, actually, let me ask you, have you guys looked at any of the midterms yet? Have you guys looked at the midterms yet, or is this your first time? First time? Wonderful. No, I'm happy, because what that means is I'm helping you guys study. My goal is by the end of these 2 review sessions, you guys should be ready to take on the exam. I don't want you guys spending all night trying to study for something. You guys got other stuff to do. So if I can help take away some of that study stress, perfect. This question right here, as you will see, is the most questionable question you'll ever see. Last year and the year before, if I were to ever get a midterm 2 question, it's always related to this one right here. Not specifically this one, but this type of question. So it says the longitudinal engineering strains on the surface of a test specimen were measured using a strain rosette to be 0.02, 0.01, and negative 0.1 along the 3 directions A, B, and C. So basically we have, and I'm going to highlight it, we have 3 strains. All right, we have 3 strains. And it says they were measured along 3 different directions. The first direction was A, which is 1, 0, B, which is 1, 1, and C, which is 0, 1. It says if the material is assumed to be in a small strain state, then the strain component epsilon 1, 1 is equal to, what do you guys think? Is it going to be A, B, C, or D? Is it going to be A, B, C, or D? Epsilon 1, 1. All right, we got B. Anyone else taking B? I made this sound scary, so no one trusts me. But yes, it's B. You got it. It's B. Because remember, for epsilon 1, 1, we are just looking at the strain along the basis vector E1. The basis vector E1 is 1, 0. So this would be the strain. So you're saying, Clayton, you hyped up this question. It's simple. Well, here's the trick. And I'm going to tell you guys the trick, and we're not going to solve it, but listen to this. If we were to take our small strain tensor, we know that in 2 dimensions, which this problem is, it's going to have 3 components. Epsilon 1, 1, 2, 2, and 1, 2. We've already said that epsilon 1, 1 is 0.02. What is epsilon 2, 2? Epsilon 2, 2 in this question. What is epsilon 2, 2? Do we have enough information for epsilon 2, 2? The negative 0.1, exactly. Because we know that epsilon 2, 2 is along the basis vector E2, and we know the basis vector E2 is C. So we know that it's going to be negative 0.01. And I'll just kind of close my bracket here. Now, question for you guys. What is epsilon 1, 2? What is that shear strain? What do you guys think? Do we know the shear strain? Our last component that we have, I'm just going to erase everything. Our last component that we have in this question is 0.01, and this is along B, which is 1, 1. Question, is that our shear strain? Who thinks yes and who thinks no? Let's see. There's no wrong answers. Well, of course, there is technically a wrong answer, but you know what I'm saying. This is how we learn. Is 0.01 our shear strain? Yes or no? Now this is why it gets hard. The question was simple because I asked for a strain that was along the basis vectors, epsilon 1, 1. But if I were to ask for epsilon 1, 2, well, of course, now things start getting hard. The trick is this. That 0.01 is not our shear strain. It's not. So our strain tensor is going to be this. Now, what do you guys think? Can I solve for epsilon 1, 2? What do you guys think? Can I solve for epsilon 1, 2 if I wanted to? Using just this information. Could I solve for epsilon 1, 2? Yes. And the answer is yes. So although this right here is not our shear strain, remember this is not our shear strain, what we do have is the strain in an arbitrary direction. And if you guys remember, we had a nice formula for that. We said that the strain in a direction dx was equal to dx dotted with the strain tensor multiplied by dx divided by the norm of dx squared. If I were to look at this equation, is our only unknown going to be the shear strain? Yes. So if you guys were ever to ask for the shear strain, epsilon 1, 2, you go to this equation right here. dx in this particular case is the direction, which we would have as 1, 1. And we know that the strain along dx is equal to 0.01. We have everything we need. We can actually solve for that strain component. Now you guys can see why this is such a dirty question. It's a lot of fun. So is there any other questions about this question, or is everybody more comfortable now? All right, I'm going to assume you're comfortable. Again, I'm looking at chat. You guys have questions, just throw it out there. I'm always happy to help. So we're going to move on to the next one. It says, in a uniaxial tension test, a specimen is pulled with a positive or a tensile normal stress sigma 11, while the remaining stress components are equal to 0. If the material is a linear elastic and isotropic with a Young's modulus E and Poisson's ratio nu, then which of the following statements is true? Now, I'm not going to read them all, but here's the thing. Oh, actually, for question 9, which direction would be associated with the shear strain? That's the trick. Shear strain isn't associated with a direction. It's associated with the angle of how much our shape deforms. If you go to the lecture notes where I talk about pure shear and simple shear, as you will see, the shear strain is actually an angle that our object is basically deforming. So hopefully that makes sense. You don't measure the shear strain along a direction. That's why that question is so good, is because typically students always think that 45 degrees is the shearing plane. So when they see a vector that looks like it's 45 degrees or 1, 1, they always think that's the shear strain. But shear strain is actually an angle, which is very tricky. That's why that question is so mean. I've gotten countless emails concerning that question. So I wanted to bring it up because it doesn't appear in this midterm, but you never know what you're going to get on the exam. So just wanted to make that clear. All right, so we're going to go back to this. It's basically saying which of the following statements is true. And if we look at all of the statements, all of them deal with volumetric strain. Volumetric strain. So the first thing to keep in mind is that volumetric strain, EV, is just the sum of all the diagonal strain components. Epsilon 2 plus epsilon 3. So if we want to solve this question, chances are we're going to need to figure out some information about these 3 components. Now, the nice thing for us is that all of the strain components, the stress components, they're all equal to 0, except for sigma 11. So if I were to look at my Cauchy stress tensor, and I'm going to draw it very small because I don't want to run out of room, we have sigma 11, but then the rest are going to be 0. And this is nice because if we look at stress-strain relationships or constitutive laws, basically a lot of the things start to cancel. Now, if you guys go to those constitutive laws, you guys are going to find the following. Epsilon 1, if everything is 0 except for sigma 1, it's just going to be sigma 1 divided by E. Epsilon 2 is going to be equal to negative nu times sigma 1 all divided by E. And then finally, epsilon 3 is going to be negative nu times sigma 1 divided by E, which is great because if I know those components, well, then I can actually just add them together. So we know that our volumetric strain, and I'm going to factor out sigma 1 over E because it appears in every single term, is going to be sigma 1 divided by E, 1 minus nu minus nu. Or in a more general format, the volumetric strain in this particular scenario is going to be sigma 1 over E, 1 minus 2 nu. So now that we have this, we can actually look at the question and we can approach it much simpler now that we have an expression. So it says, which of the following statements is true? First one is the volumetric strain is positive. Who thinks that's true? Who thinks that's true? It becomes hard, doesn't it? If we were to look at this first term in our equation, sigma 1 over E, it says that sigma 1, 1 is positive. So is that first term, sigma 1, 1 over E, going to be positive? Always. Yes. So the trick to this question becomes, okay, what's happening in the second term? So now I'm going to switch colors so we can really focus in on this term. In the general format, generally, so if I were to take any consideration of Poisson's ratio, any one at all, could I make this term negative? If I were to consider any Poisson's ratio, could I theoretically make that term negative? For instance, if I were to put a Poisson's ratio of 10, would that term be negative? You guys are tired? Thank you, Aaron. Yes, it is. So another thing we have to consider is that for a linear elastic isotropic material, we only have a certain range of Poisson's ratios that are valid. So what I'm going to do is I'm going to look at the two extremes. The first one is the lower bound. What's my lowest Poisson's ratio for an isotropic material? My absolute lowest. -1, exactly. It cannot be equal to -1. It has to be slightly greater than -1. But for the purposes of finding the boundary, I'm just going to put -1. If this is the case, we have 1 minus 2 times -1. Turns out this will be equal to +3, that term. Now, if I were to look at the other case, Poisson's ratio is equal to 0.5. This is the upper limit. What we'll find is we have 1 minus 2 times 0.5. We get 0. So we know that for a linear elastic material, the range of that term is going to be between 0 and +3. So now I'm going to ask you guys, does this term for a linear elastic isotropic material, will that term ever be negative? No. We looked at the ranges. We said it's going to be between 0 and 3. It's going to be between one of those two. So if that term is positive and this first term is positive, am I correct in saying that yes, our volumetric strain will always be positive? Am I correct in saying that? Yes. So if we look at the question, our volumetric strain is positive? Absolutely, it is positive. If we look at answer B, it says if Poisson's ratio is less than 0, the volumetric strain is negative. Well, technically, we already proved that wrong because we looked at the case where we had a negative Poisson's ratio and it turned out to be positive. So we know that that's incorrect. The next part was if Poisson's ratio is greater than 0, then the volumetric strain is going to be negative. Well, we said if we did have a very positive, so let's say that we had Poisson's ratio is equal to 10. Well, if this is the case, we have 1 minus basically 20, so this is -19. That is possible, but for a linear elastic isotropic material, we know that it's impossible to have a Poisson's ratio of 10. So that's another thing you have to be aware of, is that there's two limits. It's not just less than something, it's less than something, but also has to be greater than something at the same time. So hopefully that makes sense to you guys. It's a good question. Any questions about this, or are we good to move on to question number 11? All right, I'm going to say that we are good to go. So we're going to come down here. It says, in a linear elastic isotropic material with Young's modulus E and Poisson's ratio nu, the stress matrix is as follows. And it says, okay, what is the strain matrix? Basically is what it's looking at. What is the strain matrix? Now, there's a couple tricks to do this. And when you're dealing with this type of question, this is pretty mean because it wants every single strain component. So if you guys want to do it theoretically, you can go to that 6x6 elasticity tensor, but there is more simple ways to doing these things. The first one is this. All of our normal components are the exact same. Question for you guys. If all of our normal components are the same, sigma 1, 1, 2, 2, and 3, 3, will all of our normal strains be the exact same? What do you guys think? If all our normal components are the same, will all of our strains in the normal directions also be the same? Yes. So theoretically, although it looks like we have to solve for 6 different components, we actually only have to solve for 2. The first one is going to be one of the normal strains. So we know that epsilon 1,1 for a linear elastic material is going to be sigma 1,1 divided by E. Well, sigma 1 in this case is P. Minus nu times sigma 2,2 divided by E. So we have nu, sigma 2,2 is equal to P. And this is also divided by E. And then finally, minus sigma 3,3 times nu divided by E. Sigma 3,3 is also equal to P. So if this is the case, we can say, okay, in every single one of these terms, we have P over E. So I can factor that bad boy out, just like this. And we get 1 minus 2 nu. So that was actually pretty quick. And if we were to look at our options here, we can see right away that option B, as well as option C, they don't have that for our normal strain components. So we can get rid of them right off the bat. So we say, okay, the normal strains are taken care of. What about the shear strains? The shear strains. So I'm going to erase what I did up here, and I'm going to ask you guys a couple questions. If my shear strain, my shear stress, sigma 1,3 at the top corner, if that is equal to 0, what is my shear strain 1,3? What do you guys think? Zero, exactly. The nice thing about shear stresses and strains is that they're always proportional to each other. They're not intertwined like the normal stresses. Notice how in the normal stresses here, epsilon 1,1 was a function of sigma 1,1, 2,2, and 3,3. It was a function of those 3 different things. For shear, I'm just going to erase the highlighting, it's not the same. Sigma 1,2 is always proportional to epsilon 1,2, and that's it. There is no further relationship. So one of the things that we can see is that if sigma 1,3 and 2,3 are equal to 0, then our shear strains must also be equal to 0. It doesn't help us in this question because all of the options kind of account for that, but it's just something to know. What is nice, though, is that we know that epsilon 1,2 is just going to be equal to, and if you go back to these laws, it's just going to be equal to sigma 1,2 divided by G. Nice and simple. Now, the one thing that you have to keep in mind, all right, and I did this here on purpose because I want you guys to really emphasize this. When you look at those elasticity tensors that we derived, is there a coefficient in front of the shear strains? Is it just epsilon 1,2, or is there a number in front of it? When you guys expressed all your strains, oh, you see, you guys are too smart. 2, exactly. So what will happen is a lot of students will use this. They carry it out, but they get the wrong answer. The reason why? Because there's a 2. Whenever we're dealing with those shear strains, we have to make sure we include that 2. So what happens is we can say, okay, sigma 1,2, well, if we look at top, that's just equal to P. And we can expand our shear modulus as E divided by 2 multiplied by 1 plus nu. This just comes from the actual definition. So what you end up seeing is that 2 epsilon 1,2 is equal to P times 2, 1 plus nu, divided by E. And we can see really quick, and I'll just get the pink out, that the 2 here cancels with the 2 in here. So epsilon 1,2 is equal to P over E, 1 plus nu. And if we were to look at our different answers, we can see that this is actually answer A. So how was that for you guys? Was that too bad? It looks worse than it actually ends up being, which is kind of nice. All right, you guys are hopefully doing well. Perfect. Let's go on to the next one. Now, again, there are certain things that Dr. Sammer liked to test that I don't test, and the second one is going to be pipes. So you guys had this on one of your assignments. So theoretically, you could solve it, but I'm going to let you guys know right now, I am not going to test you guys on pipes. So that's another little hint for the exam. I'm not testing you guys on pipes. We didn't really talk about it. It appeared on your it appeared on your assignment once, but other than that, we didn't really talk about it, so I'm not going to test it. The nice thing is that it's actually pretty simple, and this goes back to the assignment. We said that if we have this condition where we had a pipe that had capped ends, like it does here, so basically it's just a pressure cylinder or a tank or something like that, we know that it's going to have two stress components. Sigma 1, which is just going to be P times R divided by 2T. And what's nice is we have every value. So P is 4. The radius in this case is 2 divided by 2, which is 1. And then divided by 2 times T, which is 0.01. So you can solve it right away to get 200. And we said that sigma 22 is equal to PR over T. Again, we have all the values. It's equal to 400. Sigma 33, we said for these thin-walled pipes, it's approximately equal to 0. So if we were to look at the three tensors, the stress tensors that reflect this, it's going to be tensor D. Again, I will not test on pipes. We didn't cover it enough, so I think it would be unfair to test you guys on pipes. But if you guys want to learn how to do it, that's all you guys would do. It's a pretty simple question. So is there any questions so far, or is everyone still doing pretty good? All right. I'm assuming pretty good. Let's move on. Question 13. We didn't really talk about this. But to me, I feel like this would be fair game in an exam, personally. I would say that this is fair game, but I will just tell you that I'm not asking a question like this. You won't see a question like this on the exam. It would be fair game because it's covered in the quizzes, but I'm not going to test you guys on this. So let's just see really quick. It says let A, which is a vector x, where x is equal to t, where t can be any real number. Basically, it's saying, what does this represent? So A, B, C, or D. What do you guys think? If you guys had to pick one. Again, I'm not going to test this on the exam, but if you had to pick one, which one would it be? A? Any other takers? No? You're all alone, Jared, but you're lucky because, yes, it is A. Because if we were to actually go to three-dimensional space, and we were to look at the coordinate points that this creates, what we'd see is that we'd have, let's say, 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3. So we end up getting basically a line. We can't actually get a point that's not off of the line because let's say this point right here, 1, 1, 2, well, that doesn't fit in with our actual vector definition. So this would just be a line in three-dimensional space. So nice job, Jared. Bonus marks if I had any to give, but unfortunately I don't. All right, so let's go on to this type of question. This is a good one. Question 14. An object expanded such that the original position is x, which is x1, x2, x3. And the final position vector, small x, is 1.1x. Basically says, what is the green strain matrix associated with this deformation? So this is a nice, fun question because what it actually gives us, even though it's in a kind of a hidden form, is it gives us the position vector x. So we know it's going to be 1.1 x1, 1.1 x2, and 1.1 x3. So if I wanted the displacement vector, u, it's going to be the exact same, but what are all my coefficients going to be? Right now they're 1.1. What's it going to be in my displacement vector, u? (0.1). See, you guys are experts. 0.1. So it's going to be 0.1 x1, 0.1 x2, 0.1 x3, because all I'm doing is I'm subtracting big X from each one of the terms. From here, I can find my displacement gradient, namely u. And as we go across, it's going to be pretty simple. All we're doing is taking the partial derivatives with respect to big X1, X2, X3. And once you do that, you get 0.1, 0, 0, 0, 0.1, 0, 0, 0, 0.1. So it's one of those questions that it's kind of a long question, has more steps, but it's not a hard question because the numbers are so simple. Because after this, we can say that our green strain tensor, we have a nice formula. It's 1/2 of nabla u plus nabla u transpose plus nabla u transpose nabla u. The key thing here, and please don't mix this up, it's another little hint for the exam. Be very, very careful of what they're asking you for. In this particular question, it says the green strain matrix or green strain tensor. So we have to include these little end components right here. If it wanted the small strain tensor, we wouldn't actually include those components. So it's something to keep in mind. What's nice for us is that if we are looking at this particular tensor, there are no shear components. So nabla u is equal to nabla u transpose. So I'll just make a little note. We have no shear components. So if we were to go through and you guys were to just do this really quick, we can find something like epsilon 1,1 really quick. It's just 1/2 0.1 plus 0.1 plus 0.1 squared. And what you end up getting for it is 0.105. So if we were to look at the different options, we can see that it is going to be D. Now this is very interesting. So notice how the other options always look very similar. If we look at options A and B, well, let's ask you guys. Let's see if you guys can find the trick. A and B don't have any crazy decimals. What do you think A and B are? What do you think they're associated with? Small strain. Exactly. Small strain. What do you think C is associated with? How would I have gotten tensor C? Notice it's the exact same, but now we have a 1 instead of a 0.1. What do you guys think? See how this is 1.105 rather than 0.105? Does that look familiar? Perhaps up here? So that's what kind of happens in these strain types of questions. Basically, if I'm asking for a particular strain, usually what happens is you give a position function. And the first mistake students might make is that they use the position function to find the strain. Well, that will end up giving you answer C. Another thing is I asked for the green strain, so if you use the small strain, you end up with answers A and B. It's always kind of one of those 4 cases, which is kind of fun. Kind of mean at the same time, I guess, but kind of fun. All right, question number 5. Another little hint for you guys, I will definitely be giving you a question like this. The hard thing about momentum balance is it becomes very complex. So if I wanted to give you a regular momentum balance question, it's going to be pretty complex. I'm not for giving you guys crazy complex answers. So this is about what you'll see, and if you guys remember from your assignment, it's honestly the exact same as your assignment. It says the stress matrix of a function, as a function of the position in a continuum has the following form, where A, B, and C are real numbers. If the body forces vector applied to the continuum is equal to 1, 0, 0, then the stress matrix to satisfy the differential equation of static equilibrium is, and basically we're asking for the coefficients. But I want to highlight something. If we have static equilibrium, static, what should our acceleration vector be? What is our acceleration vector going to be? 0. Exactly. So that's the kind of the first thing. Oops, that was that green. Let's switch back. Acceleration vector is equal to 0. Now, solving for these coefficients is actually not too tough at all. The first thing that we always check, or we should always check because it's perhaps the simplest check, is symmetry. Those two components that I circled, sigma 1, 2 and 2, 1, should they be equal to each other? Should those two components be equal to each other? Yes. Remember, our matrix has to be symmetric. Bonus question. Bonus question. Under what kind of law or statement, why is our matrix symmetric, our stress tensor? What proves that it is symmetric? Does anyone remember? Balance of angular momentum. Exactly. So you guys are ready for the test. So we said, okay, since symmetry, we know that C times x1 has to be equal to B times x2. And this has to be valid for any C or B. Or sorry, x1, x2. It has to be valid for any x1 or x2. Something like that. So if it has to be valid for all possible cases of x1 and x2, what are C and B equal to? What's the only possible way? 0. Exactly. So from here, C is equal to B, which of course is equal to 0. So if we were to look at the options, it automatically eliminates A and B. The last one that we have, of course, is going to be C and D. And from here, we have to look at our actual equilibrium equation. So I know that since this matrix is symmetric, you can go either way, but I want to ask you guys the proper way. When we're differentiating for our equilibrium, are we going horizontally or are we going vertically? Do you guys remember? For our equilibrium equation. Vertically, exactly. So all we're going to do is we are going to look at those three components and we are going to differentiate each one with respect to big X1, big X2, and big X3. Or I guess in this case, just X1, X2, X3. So let's look at the first one. We're going to take alpha x1 minus 6x1 plus 5, and we're going to differentiate it with respect to x1. So what we end up getting is we get alpha minus 6. Because 5 differentiated with respect to x1 is just going to be 0. We say, okay, now our second component, cx1, we are differentiating that with respect to x2. So what is cx1 differentiated with respect to x2? What do you guys think? What is this component here differentiated with respect to x2? Zero, exactly. So this is going to be plus 0. And then finally, we have our third component, which is 0. So we know that this is also going to be plus 0. Now we said, okay, if this is static equilibrium, this must be equal to 0. So of course, alpha must be equal to 6. Did I forget something? Yep. What did I forget? Body forces, exactly. So the last thing to keep in mind is that our equation is 3 differentials, but then plus our body forces vector. So I'm going to erase this. It's plus our body forces vector, and as we can see, we know that rho b1 is equal to 1. So we have plus 1 is equal to 0. Therefore, A, or is it A or alpha? I guess it's just A. A is equal to 5. So it's going to be this right here. It's going to be answer C. How does that sit with you guys? Not too bad? Don't forget the body forces. I've seen it happen quite a bit. You guys are too smart. So I have complete faith that you guys will do just fine with that. Question 16. As we can see, this is topics from midterm 1, so this will not be covered in our midterm, so I'm just going to put an X through it. But let's see what you guys remember. It says, let Q be a rotation matrix. Rotation matrix. What is my determinant of a rotation matrix? 1. Exactly. So there's the key. Rotation matrix, determinant's equal to 1. It says if D, E, and F are vectors, then the following is a correct statement. So basically, which one of these is true? D dot E is equal to E dot F, which is equal to D dot F, which is equal to 1. Is that true? What do you guys think? Is that true? No. What should it be equal to? 0. Exactly. So this is equal to 0. That's not true. D dotted with E cross F, which is basically a determinant, is equal to plus or minus 1. Is that true? No. Because we already said above, the determinant for a rotation matrix is equal to just positive 1. So it's going to be equal to C. If I were to just say that Q was orthogonal, all right, just orthogonal, would B be a correct answer? If I just said orthogonal and I didn't specify rotation or reflection. Yes, exactly. See, you're too smart. But again, don't worry, that stuff will not be on the actual test. These questions. I know that students love these questions whenever you're given a little cube. So it says, before any deformation is applied, the cuboid has dimensions as shown in the figure below. A deformation described by the following small strain matrix is applied to the cube. What is the length of GF before deformation? So if we look right here, we have G, we have F. So basically, what is the new dimension of this line? So the first thing that we have to remember is that the new length of a line, which I'll call L, is equal to the original length of 1 plus the strain of that line. So as we can see, it's not too bad. It's going to be equal to 2, that's its original length, 1 plus the strain. All we need to answer this question is just the strain. What is the strain that I should use? Let's see if you guys know. What is the strain that I should use? What do you guys think? Any guesses? (0.01). So that's this one right here. That is correct. That is correct. What's nice is this. We know that in general, okay, I'm going to come down here because this is going to be for the next question. We said that we can find the strain in a direction as dx dotted with E dx divided by the norm of dx. So in general, we can use this, and I messed up the beginning. This would be the strain in the dx direction. So if you wanted to, you could use this formula for the question above. It's perfectly valid. It will give you the right answer. The key thing to keep in mind is that if we were to look at this right here, our dx is going to be basically 2, 0, 0. And the strain is based on direction. It's not based on the actual magnitude. Is the direction, and let's just make it simple. So we know that this is essentially 1, 0, 0. Is that a basis vector? Is 1, 0, 0 a basis vector? Yes. We know that in this case, the direction we're looking for in terms of our strain, that's just the direction E1. So we know that for this particular case, all we're doing is looking at the strain in the E1 direction. If we look at our strain tensor, epsilon 1, 1, well, that's the very definition of epsilon 1, 1. So for this particular case, all it's going to be is 0.01. And if you were to throw that into your calculator, what you will find is that the length L is equal to 2.02 units. So we know it's going to be answer B. It's really nice. Really nice. It's supposed to be one of those trick questions. Again, let's say that you completely forget. You can go down to that formula that we have down below and you'll be able to solve everything just fine. But if you know the tricks, it can help you solve it much quicker. But let's go down. It says basically the same question as before. But now instead of GF, it wants OC. So if we look, we have point O, we have C up here, and we're basically looking for the deformation of this line. Now question, is that line along any of the basis vectors? Is that line along any of the basis vectors? Or parallel to? The answer is no. Of course. You guys are laughing. St. Clair, of course we know it's no. It's a diagonal line. So if that's the case and you were to do the strain in an arbitrary direction, this formula right here, this is going to be your best friend. So if we were to look at this line, we know that our vector, or I guess I'm going to put dx. We know dx in this case is equal to, does it go any component in the E1 direction? Does this vector have any components in the E1 direction? No, 0. Does this component go in the E2 direction? And if so, by how much? One, exactly. It goes up 1. And then how about in the E3 direction? How much in the E3 direction does this go? 1, exactly. That's the first trick. If you don't get this vector right, then everything else starts going out the window. So it gets really bad. So okay, now that we got dx and we have our strain tensor, which is right here, we have everything we need. So basically we're going to have dx, which is 1 comma, or I guess, sorry, it's 0, 1 comma 1. And we are going to dot it with epsilon times dx. So if we were to look at epsilon times dx, it's the first component would be 0.01 times 0. Well, that's 0. Plus 0 times 1, 0. Plus 0 times 1, that's also 0. So this, of course, is going to be equal to 0. I'll erase it. We can do the same thing for the second component. 0 multiplied by 0, 0. 0.04 multiplied by 1, well, that's going to be 0.04. And then 0 times 1 is also just 0, so that'll be it. And then our last one, of course, if you go through, is negative 0.01. Just like this, nice and simple. But of course, we have to divide by the norm of dx squared. So let's see what you guys think. What is the norm of dx? What do you guys think the norm of my vector above is? Root 2, exactly. Root 2. So if I were to take the norm of dx, which is root 2, and then we're going to square it, well, we know it just becomes 2. So if you do all the fancy math, what you guys will find is that this is equal to 0.03 divided by 2. And then what we have to keep in mind is that we are looking for the new length. So L is equal to L naught plus 1, all right, 1 plus the strain. What is my original length of OC? Is it OC? Yeah, OC. What is my original length of OC? Root 2, exactly. So that's another thing to keep in mind. And I'll put this in pink right here. The magnitude of a vector is also the length of the vector. The length of the vector. So if we have a vector that goes from O to C or vice versa, the magnitude is actually that length. This is going to be equal to root 2, 1 plus 0.03 over 2. All the answers are in terms of root 2, so we just need that component at the very end. And if you guys were to do the quick math, which is very, very fast, you guys will see that this is 1.015. So if that's the case, the answer is going to be A. Any questions? Still so far so good? Wonderful. Oh. So if we normalize dx, that formula would not give us the correct answer, right? It would. So that's kind of the trick. Although it doesn't look like it, this formula doesn't matter. Dx is simply just a direction. So you can normalize it or not normalize it. It's all going to be the same. Because what happens is, if we were to normalize it, the dx changes, yes. It would become smaller. But then so would this bottom term. So it doesn't matter if you normalize it. That's a great question. Anytime you ever have a vector on top with the norm down below, that's basically screaming that it doesn't matter, because the formula itself actually normalizes it for us indirectly. That's kind of a secret. That's why above here, if we were to look at dx above, technically it's not 1, 0, 0, it would be 2, 0, 0, right? Because the length is actually 2. The only reason why I said, well, it's actually equal to 1, 0, 0 is because they're the same thing. This formula relies upon just solely direction. And in this case, the direction's the same as 1, 0, 0. I was able to make that comparison. That's a great question. Yeah, makes it easier for us too. All right, question number 19. It's kind of a longer one. It's basically the same thing before, except this time instead of giving a strain, it gives us the state of stress. Now it says the cuboid is made up of a linear elastic material with a Young's modulus of 2 GPa and a negative Poisson's ratio of negative 0.1. The length of the vector OG after deformation is, so basically OG is going to be this line right here. So if we were to look at this line, first question, is it aligned with one of the basis vectors? Yes. So if I want the strain for this line, what strain am I basically looking for? What strain do I need to solve this question? What do you guys think? What strain do I need to solve this question? 3, 3. Exactly. It's along, and I'll highlight it here, it's along basis vector 3, 3. Therefore, I need epsilon 3, 3. What's nice for us, for our linear elastic materials, we have a very nice expression. Epsilon 3, 3 is equal to negative nu times sigma 1, 1 divided by E minus nu times sigma 2, 2 divided by E, and then plus sigma 3, 3 divided by E. Are we given the Poisson's ratio? I know it's a trivial question. Maybe I shouldn't have asked that. We are given the Poisson's ratio. We are given the Young's modulus. And we are given sigma 1, 1, 2, 2, and 3, 3. So the better question is there any unknowns in my equation? Are there any unknowns? No, exactly. So it's basically just plug and chug your way through. So negative, our Poisson's ratio we said is negative 0.1. And sigma 1, 1 from above is 200. Now for our Young's modulus, it says it's 2 GPa. So based on how I entered sigma 1, 1, what should I input for my Young's modulus? What should I have on the bottom? 2000. See, way too smart. You guys got this. Over 2000. Move on to the next one. It's minus negative 0.1 times sigma 2, 2, which is 200. And then again, it's divided by E, which we said is 2000. And then our last one is negative 100. This is over 2000. And what happens is you will get that all of this is equal to negative 0.03. And once you have the strain, everything is good to go, because L, our current length, is going to be our original over 1 plus E. So it's basically going to be 1 unit, which we had before, over 1 minus 0.03, which is equal to 0.97. Not too bad. How was that? See, it's a lot of fun. Once you guys know these constitutive laws, you can solve anything. It's quite wonderful. All right. Next question. This is a very fun question. It's one of those questions that students will either know right off the bat, or they go to my lecture notes and find it right off the bat. So basically we have a square, and as we can see, we've deformed it such that it is shearing. So it goes back to the old question of what is shear strain? Well, basically shear strain, that's this angle. The angle it starts to shear. So basically it's asking for what is the position function that would describe this. Now, the first thing that you're going to have to keep in mind is that when we shear something, are we shearing it on both ends? Basically, do we have this scenario that we have drawn, or, oops, that was a highlighter, or do two ends stay the same and we have this scenario? So that's kind of the first one. One is simple shear, one is pure shear. Now, what's nice is if you guys don't know this question, my lecture notes kind of describe it perfectly. I show you the two scenarios and I show you the two outcomes. Now, if we were to look at the two things down here, we see a couple different things. The first one is some of the answers have it on both components, and some of the answers only have it on one. So notice how in part B, one of the shear components is 0, while the other one is alpha. So I'm going to give you guys the first question. Should I have both components non-zero, or should only one of the components be non-zero? What do you guys think? For that particular case that we are shown above, should both components be 0 or just one of them? Or sorry, both components be non-zero or just one? Both, exactly. If we were to have one of them as 0, it goes back to the other case of this, where we have something that's like this. Because if we were to look here, we have alpha on this side, and we don't have alpha on the other side. So right away here, we can start to eliminate B, and we can eliminate C. Now here's the trick. Here's the special trick. The actual shear strain is the tangent of alpha. Tangent of alpha. And the trick to this question says alpha is a small angle. So if we have small angles, what is tangent of alpha approximately equal to? For small angles, alpha, exactly. For small angles, tangent of alpha is approximately equal to alpha. Therefore, the answer is going to be D. How is that? Not too bad. Again, it's one of those things that if you forget my slides, I have it directly covered so you can just go straight to there. But I wanted you guys to try and solve it, and well, I guess joke was on me because you guys solved it really fast. You guys know exactly what you're doing. Question 21. The shown beam has a constant width of 1 unit and a height that varies over the equation. So if we look, or according to the equation. So if we look here, we have H as this equation. We know that the in-plane thickness is 1. So what is my area equal to? Is it just equal to my height? Is my area just equal to my height in this particular case? If that thickness is 1. What do you guys think? Exactly. Area is equal to base times height, and in this case it's just going to be equal to 2 minus x1 squared over 200. So we're going to get that out of the way really quick. It says the beam is subjected to a horizontal body force that is equal to rho g and units of force per unit volume, and the following boundary condition of value p. If sigma 11 is the only non-zero stress components, which of the following is the differential equation? Now what's nice about this, and I'll give you guys a couple hints here. Did you guys cover basically this exact example in your lab or in your assignment? Differential equation with stress. You guys remember? What do you guys think? Did you cover this basically directly in the lab or assignment? Yes. Would I ever give you on an exam a scenario that has a different differential equation you've never seen before? What do you guys think? You think I would do that to you guys? No. Turns out this right here is going to be the exact differential equation from your lab. If you guys go back to your lab, you'll see that it is A times d sigma over dx plus sigma dA over dx, and then plus rho GA is equal to 0. So if we look here, do we know what our area is? Do we know what our area is? What do you think? Do we know the area? Yes, exactly. I know you guys are rolling your eyes at me. Like, of course we do, Clayton. Come on, wrap it up. We have it above. Can I find the differential of area with respect to x? Of course I can. If I have area, all I have to do is take the differential, which is 2x1 over 200, I guess negative, which is equal to negative x1 over 100. So from here, it's just a matter of plug and chug. If we look at answer A, it has the Young's modulus. So let's just get rid of that because that is nowhere to be seen. If we look at answer D, we have P. P doesn't appear in our boundary, or sorry, it doesn't appear in our differential equation. What is P used for? What is that stress at the end of the beam used for? You guys remember? What is that concentrated load used for? Boundary condition. Exactly. Now, last question. What is this term right here? Negative x1 over 100. Is that my area or is that my dA, my differential of area? It's equal to dA, exactly. So if we look at equation B, we have dA multiplied by d sigma. Well, we know that's incorrect. It should be A multiplied by d sigma. So we know that the answer is C. It's basically just finding those components and then comparing them with the actual equation. So hopefully that wasn't too bad. Next one's a fun question. This is the end. These are the last questions. 23 and 24 are just straight theory, so we're almost done. Hold in there, guys. I know you guys want to go watch the Oilers game, but we'll be done way before it happens, so you don't have to worry. All right. So it says, which are the relationships between uniaxial engineering strain and the uniaxial green strain is true? All right, well, this isn't too bad. What we have to do is we have to start off with the green strain. We know that the green strain is equal to 1/2 lambda squared minus 1. Now on the other side, we have our engineering strain, which is just lambda minus 1. So the first thing I like to do is I just write them out. I got this equation and I got this equation. And what I want to do is I want to try and find a way to have this term inside of my other equation. So I can say, okay, my green strain is equal to 1/2. And question for you guys, can I expand this? Can that right there be expanded? Yes, exactly. So if I were to expand this out, we can have lambda minus 1, lambda plus 1. Now it gets fun because if we were to look right here, we have a lambda minus 1, and we know that is actually equal to our green strain. So this is equal to 1/2 of my my engineering strain, lambda plus 1. So we know it's going to be answer B. One of those fun little questions. Not too much crazy math, so hopefully it's not too bad. All right, last two questions, which is good because my voice is starting to go away. Question 23. The matrix representing the stress at a point inside a continuum is symmetric as a result of, so the key thing here we're talking about our stress matrix, our Cauchy stress tensor sigma. What do you guys think? Is it because our strain is symmetric, the law of the balance of moments, the body is linear elastic, or the material conserves energy? A, B, C, or D? What do you guys think? B, exactly. The most correct term is the balance of angular momentum, and if you guys look at the lecture notes for that, all we did was we did summation of moments. So this is actually going to be B. The balance of moments are basically, I'll put in brackets here, angular momentum. All right, last question. In a linear elastic structure, the matrix of coefficients relating the stresses to the strains is symmetric because of, what is this right here? Is this our strain matrix, our elasticity tensor, our stress tensor? What is that? What is the matrix of coefficients? Stiffness, exactly. So basically, stress is equal to a tensor C times strain. And we are talking about this matrix in right here, the one that relates stresses to strains. So it gives us four options. The strain matrix is symmetric. The stress matrix is symmetric. Both the stress and strain are symmetric. Or B, the material conserving energy. A, B, C, or D? What do you guys think? Why is our stiffness matrix symmetric? A, B, C, or D? D, exactly. Remember, it's number one trick, and I said it a lot in the lecture. I'm going to say it a lot again now. It's very easy to think that C is symmetric because everything else is symmetric, but that's not true. C is only symmetric because we have a linear elastic material, or basically an elastic material. It conserves energy. Basically, my loading and unloading path are the exact same. So that's why it is. And that's it for 2014. You guys were too smart. Every trick I tried to ask you about, you guys knew directly. So I'm not sure how much I helped you guys out. And again, you guys just seem like geniuses. But yeah, that concludes the little lecture tutorial, or I guess review session. I don't know what to call it. I hope you guys learned something. I hope I didn't waste your time. With that being said, I'll let you guys go for the night, and I will see you tomorrow morning for beams under axial load. It's going to be a lot of fun. And tomorrow's review session will start at 5:30. Question, would you prefer even later? Would you guys prefer like 6 o'clock, or is 5:30 probably the best time? What do you guys think?